Hello, in the video invitation to the theory of music, which aims to motivate you to study this theory, we presented some details of the production of sound on a vibrating string using a single stringed instrument. In this video, we will expand this study. Remember that a series of tones, called modes, are produced simultaneously, with frequencies given by the relationships shown above on the right, and that their amplitudes depend on the way in which the string is plucked. The first of these modes, corresponding to n equal to 1, is the fundamental tone with a frequency f1, and the rest are harmonic tones with frequencies multiples of this fundamental frequency. The expression for the value of these frequencies justifies the fact that in stringed instruments the thickest string, of greater mass μ per unit length, is used to produce the lowest frequency, and that this thickness is decreased in the remaining strings to produce higher frequencies. It also justifies the fact that a peg mechanism is employed for the precise tuning of these strings by varying their tension T. Then we will pull the string at a distance of 1/3 of its length measured from the bridge of the instrument, to produce the deformation shown in the figure. In this particular case, the amplitudes of the harmonics are given by the relationship shown below the equation for the frequencies. When the string is released, a vibration will be produced, which is the result of the sum of a series of sine-shaped vibrations whose amplitude varies with time and which present their zeros at the ends of the string, and in equal divisions of its length, which will be called modes of vibration of the string. The first mode will present only its first half cycle and will give rise to a frequency called fundamental, the second 2 half cycles and will give rise to a frequency equal to twice the fundamental, the third 3 half cycles and will give rise to a frequency equal to 3 times the fundamental, and so on. These frequencies are called harmonics because, as we will see in this experiment, they retain the essence of the sound of the fundamental. In general, an infinite set of harmonic modes will be produced, but for the deformation impressed here to the string there is no contribution of the third harmonic, since for it the argument of the sine function that constitutes the last term of the formula for its amplitude is pi, and according to the video in which we study the sine function, this one is null for multiples of pi. Next, we consider the modes of vibration of the string in the ideal case where there is no attenuation of its movement. The vibration of each mode is shown, but we will begin by reproducing only the sound of the first mode, corresponding to the fundamental frequency, and then we will sequentially add the sounds corresponding to the rest of the modes of harmonic frequencies, so that you can appreciate the sonorous contribution of each of them to the sound emitted by the string. You will notice that this sound will become richer and richer, but that it essentially corresponds to the same tone. We have concluded the first part of our experiment. The fundamental result obtained is that the sounds of the harmonic modes resulting from plucking a string form a set of the same class, in this case, the sound of the C note. Now, the sound we obtained in this part of the experiment does not resemble the sound we normally get when plucking a string of an instrument such as the guitar or the ukulele. Remember that we have considered the ideal case where there is no attenuation. In the case of a real instrument, part of the energy is transmitted to the instrument, originating a gradual decrease that we will model in the second part of this experiment in a simple way, by means of an exponential attenuation coefficient. Next, we will consider the modes of vibration of the string in the normal case of attenuation of its movement. We will start by reproducing only the sound of the first mode, corresponding to the fundamental frequency, and then we will add the sounds corresponding to the harmonics. The resulting sounds are now similar to those obtained when plucking the strings of instruments such as the guitar or the ukulele. The results of this second part of the experiment corroborate the results of the first part. Therefore, in the following video, dedicated to the search for musical notes, we will focus on finding sounds that have a harmonic relationship with the note C. This experiment also reveals that by choosing the point at which the string is plucked, the player of a stringed instrument has some control over the sound produced by this instrument, which can be used to give a personal stamp to his performance. Thank you for watching this video. We look forward to seeing you in the next one, dedicated to the search for musical notes, which is a logical continuation of this one and adds value to it.